Good morning, all of you. I am Dr.J.Vinnarasi, Assistant Professor of Chemistry, the Standard 5X Rajaratnam College for Women, Sivagasi. Today, we are going to see about the topic VSEPR theory, that is valence shell electron pair repulsion theory. So, the theory was initially suggested by Sedgwick and Powell in the year 1940. Later, it was developed by Gilibus and Nilgom in the year 1957. But initially, we told that the theory was extended, the Sedgwick was extended the theory of Lewis. So, the theory is based on the polyatomic molecules in the direction of bond around the central atom. So, it depends upon the number of bonding as well as non-bonding electrons in the valence shell. So, this theory is based on only for polyatomic molecules, not for the transition metals. So, the assumptions or the postulates of the theory is the shape of the molecule is determined by the repulsion between the electrons present in the valence shell. So, the electron pairs in the valence shell of the central metal atom repel with each other and align themselves, or they allocate that space, the stereo space, to minimize their repulsions. Most probably, the lone pair electrons takes much space or take more space around the central atom than the bond pair electrons. The minimum repulsion to the state minimum energy and the maximum stability of the molecule. Maximum stability of the molecule. So, the presence of lone pair in the central atom causes slight distortion of the bond angle from the ideal angle. The magnitude of the repulsion between the bonding pairs of electron depends upon the electronegativity difference between the central atom and the other atoms. So, the repulsion strength depends upon the order, the lone pair and the lone pair and the bond pair, because the lone pair takes much space or more space to the central atom, and the bonding depends upon the repulsion is the triple bond takes much repulsion than the double bond and the single bond. So, the steps are the rules for the prediction of the geometry. First, determine the central atom. Second one, draw the electronic dot structure from the Lewis. Third one, find the arrangement of the electron pair. Fourth one is the find arrangement of the bonding pairs. The last one is the determining the geometry based on the bonding pairs. So, these are the steps to predict the geometry of the molecules, or these are the rules framed by the scientists who determine the geometry. First, we determine the central metal atom. So, we saw some examples. Based on the examples, we have easily predict the geometry of the molecule. So, based on the bond pair electrons, the geometry may be. For example, we consider the molecule beryllium hydrate BeH2. So, beryllium, the electronic configuration is 1s2 2s2. So, there are 2 electrons in the valence shell electrons. So, based on the bond pair electrons, the geometry may be linear. There are no unpaired electrons. So, these examples is based on the bond pair electrons only. The central atom is beryllium. The electronic configuration of the beryllium is 1s2 2s2. So, predicting the geometry, we have to set the central metal atom. So, from this molecule, the central metal atom is beryllium. The 2 other atoms are hydrogen. The electronic configuration for the hydrogen atom is 1s1. So, the geometry of the molecule is linear and the bond angle is 180 degree. Second example, the central atom with the 3 bond pair electrons. The example is boron trifluoride. So, this is a electron deficient compound. The electronic configuration, we set the central atom. The central atom is boron. So, this type is AB3 type molecule. The electronic configuration of the boron is 1s2, 2s2, 2p1. The valence electrons present in the valence shell are 2p2 2s2 2p1. So there are 3 bond pair electrons. So the geometry is trigonal planar arrangement. The bond angle is 120 degree. The next example is the central atom with 4 electron pairs. The geometry is tetrahedral. For example, we consider the example methane molecule. So the central atom present in the molecule is carbon. The electronic configuration of the carbon is 1s2, 2s2, 2p2. So the valence shell electron is, in the valence shell there are 4 electrons, 2s2, 2p2. So the molecular geometry is tetrahedral. The bond angle is 109.5. So the easy method to predict the geometry is calculate the valence shell electrons. There are 4 electrons. Then there are 4 hydrogen atoms, each having 4 electrons in the valence shell. So totally 8 electrons. We have to calculate the hybridization. So 4 plus 4, 8 electrons. So 8 electrons are below electrons. We have to divide the number valence electrons by 2. We get 4. So the hybridization is sp3 hybridization. The bond angle is 109.5. So the methane molecule is tetrahedral in structure with the bond angle of 109.5 degree. So the next example is the central atom with the 5 electron pairs. So we have taken the example phosphorus pentachloride. The central atom is phosphorus. The electronic configuration of the phosphorus is 1s2, 2s2, 2p6, 3s2, 3p3. So the valence electrons is, there are 5 valence shell electrons, 2s2, 3s2, 3p3. So the molecular geometry is trigonal bipyramidal geometry. The bond angle is 120 as well as 90 degree. The next example is central atom with the 6 bond pair electrons. We consider the example S of 6. So we simply calculate the hybridization using the simple method. The valence electron in the sulfur atom are 6. Then we have 6 neighboring atoms. The neighboring atom is fluorine. The valence electron in the neighboring atom is 7. So 7 into 6, that is 42. 42 plus 6, 48. So 48 divided by 8, we get 6. So the hybridization is sp3d2 hybridization. So we expect the geometry of octahedral geometry with the bond angle 90 degree. So we consider the example of central atom with the 6 electron pairs. So the geometry is octahedral according to VSEPR theory. So the central metal atom is sulfur. The configuration, the electronic configuration of the sulfur is 1s2, 2s2, 2p6, 3s2, 3p4. So the electrons present in the valence shell are 6 electrons, 3s2, 3p4. So we get the molecular geometry of octahedral geometry with the bond angle 90 degree. So next we consider the examples or geometries. Depends upon the bond pairs as well as lone pair electrons. Previously we saw the geometry of the molecules or the polyatomic molecules with bond pairs only. So the shapes of the molecules containing bond pairs as well as lone pair of electrons. So next we see about the example, the central atom with the 4 electron pairs, 3 bond pairs, 1 lone pair. The example is ammonia molecule. So the central atom present in the molecule is nitrogen. The electronic configuration of the nitrogen is 1s2, 2s2, 2p3. There are 5 electrons in the valence shell, 2s2 and 2p3. The molecular geometry of the molecule is trigonal bipyramidal. But the electronic pair arrangement of the molecule is tetrahedral because there are 3 bond pairs and 1 lone pair. So the presence of lone pair causes the slight distortion from the bond angle because the bond angle of the tetrahedral is 109.5. Due to the lone pair present in the molecule, they changes into 109 to 107. because the lone pair accumulate much space to the central atom. Next example, the central atom with 4 bond pairs and 2 lone pairs. The example is water molecule. So the central atom present in the molecule is oxygen. There are 6 valence electrons. So the molecular geometry of the water molecule is V shape or bend shape. But the electronic pair arrangement of the water molecule is tetrahedral. The repulsion between the lone pair and the lone pair bond pair is possible. So this repulsion causes slight changes in the bond angle, because one lone pair, the bond angle differs from 109 to 107 in ammonia molecule, but in water molecule there are 2 lone pairs. So the lone pairs much distortion from the bond angle from the tetrahedral 109 to 104.27. So the water molecule is bent shape or V shape with a bond angle of 104.5 degree. Next the example is the central atom with the 5 electron pairs with the one lone pair. That is geometry is seesaw. The example is SF4. So according to hybridization, the hybridization may be vary because the electron pair arrangement causes trigonal bipyramidal geometry. So the hybridization is sp3d geometry, but due to the lone pair repulsion we get the distorted geometry, that is seesaw geometry or distorted octahedron geometry because of lone pair repulsion. Due to the trigonal bipyramidal geometry, the bond angle expected is 90 degree as well as 120 degree. But due to lone pair bond pair repulsion, the bond angle may be differs. The next example is the central metal atom with the 6 bond pairs. So there are 4 bond pairs with the 2 lone pairs. There are 6 bond pairs means the expected geometry is octahedral, but due to 2 lone pairs, the expected geometry is square planar. The central metal atom of the molecule is xenon. So the valential electrons are 8. Due to bond pair lone pair repulsion, the geometry may be differ. The molecular geometry occurs in the molecule is square planar, but the electron pair arrangement is octahedral. The bond angle is 90 degree. So due to the effect of electronegativity present in the atom, the bond angle may be differ. Because we saw the example of ammonia, we get 107 degree Celsius trigonal pyramidal geometry, but due to the molecules, the atoms and electronegativity, the molecular geometry of the nitrogen molecule, the bond angle may be differs, because the more electronegativity atom distort the molecule, lone pair molecule, because the lone pair molecule has take much space to the central atom. So due to ammonia, the bond angle is 107.48, but the geometry is trigonal bipyramidal, NF3 also getting a trigonal bipyramidal geometry, but the bond angle differ from 107 to 102 due to the bond pair lone pair repulsion. So this is the diagram which represents the VSEPR theory with the bond pair as well as the lone pair. So what is the limitation? It fails to predict the geometry of isoelectronic species. For example, CH4 as well as NH4 ammonia, both are isoelectronic species, but they cannot predict the shape of the molecule. Second, they cannot explain the transition metal complex, because VSEPR theory explains the polyatomic molecules, not explains about the transition metal complex. Then third one is that the model does not explain the relative size of the substituents, because they explains about the electronegativity of the atoms. They are unable to explain the atomic orbitals overlap. So these are the limitations of VSEPR theory. Thank you.